Imagine a machine so precise that it can detect a target from kilometers away, calculate its position in fractions of a second, and continuously correct its path while traveling faster than the speed of sound. Most people see the missile. Almost nobody sees the tiny guidance system hidden inside. Yet this collection of sensors, processors, and electronics often costs more than a luxury car. Today, we're going inside one of the most advanced manufacturing environments on Earth to discover how missile guidance systems are made. Think about this. A modern guidance package contains thousands of components working together with astonishing precision. One microscopic defect can cause the entire system to fail. But here's what nobody tells you. Many of the materials inside began their journey in remote mines, deserts, and industrial plants scattered across the world. And this is where our journey begins. The story starts with silicon, the foundation of nearly every processor inside a guidance system. High-purity quartz comes from mines in countries such as the United States, Australia, Brazil, and Norway. Refineries convert it into electronic-grade silicon with purity levels exceeding 99.9999999%. A single contamination particle smaller than a grain of dust can ruin an entire production batch. Next come rare earth elements used in sensors, actuators, and specialized electronics. Neodymium, dysprosium, and other critical materials travel thousands of kilometers before reaching manufacturers. Some shipments cross oceans and multiple borders before entering secure production facilities. Most people never think about the incredible logistics hidden inside a device smaller than a backpack. Aluminum, titanium, gold, copper, and specialty ceramics also play critical roles. Titanium provides strength with low weight. Gold protects sensitive electrical connections from corrosion. Advanced ceramics shield delicate electronics from heat and vibration. Together, these materials create a structure capable of surviving extreme environments. What happens next surprised even experienced engineers. Before a single component enters final assembly, every material undergoes chemical analysis, purity verification, and traceability checks. Manufacturers track many parts back to their original source. And the next stage demands a level of precision that feels almost impossible. Inside a semiconductor fabrication facility, silicon wafers move through hundreds of manufacturing steps. Furnaces operating near 1,000 degrees Celsius or 1,832 degrees Fahrenheit create ultra-thin layers only nanometers thick. Robotic systems transfer wafers automatically because even a fingerprint contains enough contamination to destroy sensitive circuits. The air feels almost motionless, and the silence is broken only by the hum of precision equipment. Frame, picture, image. Meanwhile, precision machining centers carve aluminum and titanium housings. CNC machines spin at thousands of RPM, while cutting tools remove microscopic layers of metal. Bright sparks flash across enclosed work cells. Every surface must meet exact specifications, because even tiny alignment errors can affect performance. The inertial measurement unit, often called the IMU, represents one of the most demanding assemblies in the entire system. Technicians install gyroscopes and accelerometers capable of detecting incredibly small movements. These sensors must remain stable despite vibration, acceleration, and temperature extremes. Imagine balancing a coin on its edge during an earthquake. That gives you a sense of the challenge. Circuit boards move into automated assembly lines where robotic placement machines position thousands of electronic components every hour. Tiny solder joints form electrical connections during controlled heating cycles. The smell of heated flux briefly fills the air before powerful filtration systems remove contaminants. Every connection must survive years of storage and extreme operating conditions. Finally, engineers integrate sensors, processors, wiring harnesses, and protective structures into a compact guidance package. Components that began life on different continents now operate as a single system. But manufacturing isn't the hardest part. Proving that everything works may be even more difficult. Advanced factories rely on robots, AI vision systems, laser scanners, and automated inspection stations. High-resolution cameras search for defects invisible to the human eye. Lasers measure dimensions with micron-level precision. Every movement generates data that feeds into quality control databases. Manufacturers test for vibration, shock, temperature, humidity, and electrical performance. Some systems experience temperature swings from deep freeze conditions to extreme heat. Shaker tables simulate violent movement. Environmental chambers push components far beyond normal operating conditions. If something fails here, engineers want to know immediately. And this is where it gets truly extraordinary. Even with automation, experienced technicians still perform critical inspections. Human experts can recognize subtle patterns and anomalies that software sometimes misses. In some facilities, rejection rates remain below a few percent because both humans and machines work together. After passing qualification standards, each unit receives documentation, traceability records, and certification reviews. Thousands of measurements confirm that the guidance system meets demanding requirements. Yet the global scale of this industry remains even more surprising. The global market for missile guidance and precision navigation technologies is worth many billions of dollars annually and continues to grow as electronics become more capable and compact. The United States, China, Russia, France, and Israel rank among the major producers of advanced guidance technologies. Tens of thousands of engineers, technicians, machinists, and scientists support this industry worldwide. Did you know that modern guidance electronics often contain more computing power than systems used in early space missions? Did you know some sensors can detect motion so small that it would be difficult to see with the naked eye? And did you know that manufacturing tolerances sometimes approach the width of a human hair divided dozens of times? What seemed impossible 50 years ago now happens every day. From quartz mines and rare earth processing plants to clean rooms, CNC workshops, and testing laboratories, you follow one of the most complex manufacturing journeys on Earth. Most people never see the hidden craftsmanship inside these systems. Yet every sensor, circuit, and connector tells a story of precision, science, and human ingenuity. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the Earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.